Hello, we are Team E6 Cannonbots. For our project, we have built a multi-robot searching system intended to aid search and rescue teams in an indoor urban environment. The idea behind the system is to increase the search area that a single operator is able to cover through the use of multiple autonomously searching robots that provide real-time information on their current state. Our design from the start considered everything that we would need to properly satisfy this use case of reduction of area of search in an urban disaster site. To accomplish this, we broke our system down into 3 major subsystems that each of our team members worked on. Josh with physical design, ensuring all motors and sensors will be useful and secure. Brooks with localization, where we make use of our sensors to pinpoint where our robot is in space and transmit that data over Ross. To Adrian with his base station UI, where we give feedback with our sensor data and receive input for a full user-in-the-loop experience. Starting with our physical design, then, we have 3D printed housings that hold all of our components. The ESP32 is mounted on the front so the built-in camera can easily be used as desired for teleoperation. This allows the user to more easily diagnose situations on a bot-by-bot basis should the autonomous system ping the user, and it does so if it believes manual input is necessary for things like collision detection. Underneath the ESP, but still on the front, is our LiDAR, which we use for our autonomous obstacle detection and environment detection. On the other side of the same mountain plate, our UWB module is housed with an upright antenna, as research pointed us to this being the best orientation for localization data. On top of our motors, closest to the back, you can see where our LiDAR is connected to our system. The PCB board that you see that's red here on top of our battery serves to allow us to more easily connect our components being controlled by our ESP. In the middle of this PCB, we have our IMU, which provides us with real-time acceleration data that we use for collision detection and supports our UWB data with orientation tracking. Last, for this PCB board, we have an H-bridge that controls our motors with PWM signals from our ESP that are generated by our UI algorithm, described more in depth later. These 2 DC motors that are controlled by that H-bridge, along with a ball caster at the rear, allow for stable driving and tighter turns than a 4-wheeled robot would be capable of. This locomotion also makes use of custom gearbox to increase the RPM of the wheels from our base motor RPM. The resulting system as a whole is 0.167 meters per second and satisfies our 0.1 meters per second requirement to compete with typical SLAM systems that are within our price range.
The locationing subsystem's job is to determine the real-time positions of each robot in a 2D plane using the base station as a reference point. To achieve this, our system combines two-way ranging over ultra-wideband radio between each robot and 3 or more anchors, which are ultra-wideband transceivers that are capable of ranging between each robot. Once a robot has obtained its distance from each anchor, we use a method called trilateration to compute the coordinate of each robot. Once calculated, the robots publish their coordinates over Wi-Fi via ROS, or Robot Operating System, which the user interface can then display as the current locations of each robot for the operator, along with other sensor data.
The user interface, operating from a computer base station, provides the operator with comprehensive control and real-time monitoring of the Cannonbot system. The core display features include the current locations of each robot, which are determined by the locationing subsystem. In addition to location data, the UI presents other sensor telemetry data and the identified location of any survivor tag. For instances requiring direct control, the operator can enable live camera streams and manually navigate each robot using the computer's arrow keys in the case the bot collides with an obstacle and is unable to maneuver around that obstacle. The operator can also switch the system to autonomous search mode, choosing to deploy either a single Cannonbot or both Cannonbots simultaneously with the use of a search algorithm called frontier-based search algorithm. The frontier-based search algorithm is key to the Cannonbot's autonomous operation because it guides the robots to systematically explore the environment, and it works by labeling cells on the map as free, occupied, or unknown. The algorithm then calculates the centroid of the border between the known/free cells in the unexplored/unknown areas, which is designated as the frontier cell. And this frontier cell can serve as the direct command for the bots, which instructs them on where to go next and is continuously updated as the robot's coverage increases on the map. There are two autonomy modes where either one Catum bot does the autonomous search alone or both bots doing the search at the same time. As you also may notice during the search, the bots can also detect if the obstacle is in front of them within an 8 centimeter range within their LiDAR, using their LiDAR sensor, then move in reverse to try a slightly different direction, and then proceed to move forward again, which the cycle keeps repeating until it finally gets around that object.
I didn't really know what to write for physical housing. If you want to write something like a little paragraph about the UI, like just something short, and then we should just record that.
Okay, so what we have here is a setup of our project. We have all 4 anchors in each corner, as well as a UWB tag in the middle over there. We have our 2 Canon bots over here. They are ready to be searching. And here we have our UI. So we have both cameras on for each Canon bot, as they each have their own ESP32 camera. So this is just streaming them. And then we have a manual teleop functionality, as well as like aligning the buttons to like align properly their point clouds and the IMU orientation, because sometimes it goes off. Also, we have our autonomy controls, which I will show eventually. And then we also have our telemetry data that is reading off the sensor data from IMU UWB positioning and our LiDAR sensors. So if we just click Start Autonomy, they are doing their search. Okay, as we see here, this has collided with an obstacle. So what we can do here is, for bot 1, we can just simply teleop this manually to just put them back in place. And then same thing for bot 2. And our UI is also like basically coloring this map, just showing like the coverage of the whole search, which is the point of this project. I can just restart the autonomy, and they can keep continuing. And for example, if they like encounter something in front, like a wall, they'll try to just like move back and try a different angle that they can turn in. So it would take them probably a few iterations for them to get over the obstacle. But in the case that it just doesn't, you can always just teleop them. And assuming that you can't even see the bots, you always have this camera view of what the bot is exactly seeing. So it can help you maneuver this bot to the correct position and not just keep blindly hitting into obstacles. Oh, look, there's the other Canon bot. They're staring right into each other.